Well, um, so in this talk, I'm going to talk about our work on learning optimal representations for supervised machine learning from an information theoretic perspective. Uh, this was actually work done by an AI resident that I've worked with over the last year. And so we're going to talk about this. And so most of the slides are also like from what he made. So the slide credits go to him. And so I'm just like talking about all the awesome work that he was doing. Um, okay. So the outline of the talk is that we want to characterize what are optimal representations Z star for supervised learning. And then we'll talk about like how to approximately learn such an optimal representation. And then we will discuss two applications of the framework, which is one is that we can use the framework that we will talk about as a regularizer to improve generalization and as a predictor of generalization for neural networks which are trained. So the high level overview or the problem statement that we are considering is as follows. Consider a cat versus dog classification problem where you have an encoder that gives a representation Z. And then you have a classifier that is sitting on top of the representation that is actually going to do the classification. And so imagine that there is that you like you are interacting with a company. So the company cares about classifying cats versus dogs with predictors V. So when I say the classifier, it can be like they declare that they're going to use either a linear family or a 3-layer MLP or whatever architecture. And they declare that they're just going to minimize the loss on the training set. And then the question or the challenge for you is to learn the right representation Z that will be used by the company. And by the way, if you have any questions, feel free to interrupt and ask me. Um, so essentially, this is the setup. And the question of optimality here is what Z, so what is the right Z that guarantees that you will always reach the best achievable test loss? So that means that the right representation will ensure that the downstream classifier that the company trains will do really well on the problem of interest. And the traditional way of learning representations using deep learning, like you would normally be minimizing some cross entropy loss between your ground truth and like the predictions of and the beliefs of the model, right? So we usually call that like empirical risk minimization. So basically what that means is that imagine I'm showing you the Z space. Then if you have these two, like you have a classifier that would like so let's say the cats and the dogs with the specs are in the test set. Then a class you could learn a decision boundary such as this that would overfit in the sense that it would not generalize to test. Whereas you could also learn a decision boundary like this that would generalize such that it would like classify the cat with the specs also as a cat. And so imagine if like your V was the set of classifiers which are like vertical decision boundaries. Um, then empirical risk minimization basically has this problem that it is not optimal. That is, it does not ensure generalization. Uh, and But the benefits of empirical risk minimization are that it gives perfect predictions when the number of samples goes to infinity, where because max likelihood is optimal in the infinite data limit. And it is also sample efficient. So we have packed guarantees on estimation, and it is easy to optimize because the optimization problem we are solving is a min over the classifier and the min over the parameters of the representation. So it is easy to optimize. And so um, And so in this paper, we are going to improve on that. So imagine if you had a representation which is different from the previous one, right? So imagine if you had a representation like this, where all the cats line up together in the same sort of x coordinate. Then you see that no matter, so for this representation, all the empirical risk minimizers will generalize. So if you are able to, because there is no way for you to distinguish between the test cat which has the glass and the training cats which do not have the glasses. So if you could learn a representation such as this, then there are two properties that this representation is satisfying. The first is that it is sufficient with respect to the function family of linear decision boundaries. So what that means is that classifiers in this function class can discriminate between the two classes, and it is minimal with respect to the V that we've chosen, which is linear decision boundaries, in the sense that there is no vertical linear decision boundary that can distinguish within the examples of this class. So if you have a representation like this is optimal, and this is also sample efficient, and we have some guarantees on estimation, but the optimization is a bit finicky because this is like actually a min max problem that we end up having to solve. And so are there any questions on the intuition of what I talked about?
So I don't see any questions. So maybe I'll
Okay.
share if there is a question. Okay.
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 So this is the notion of optimality we're talking about. We would like to have a representation like this, such that for the function class that we care about, you are not able to distinguish between the examples within the same class. And so an overview of our results is that we prove some theory that the notion of V sufficiency we talked about before is the same as saying that there exists a classifier in the function family, which in our case was like the linear decision, vertical decision boundary, that predicts perfectly. And this is by definition. So V sufficiency is basically defined this way. And the notion of V minimality, which like we saw in the previous figure would bring all the cats and the dogs to align, means that all the classifiers in V will generalize. So this is basically what like sort of informally stating what I was saying on the previous slide. um, and basically the intuition for this is that if we cannot distinguish within a class with our function family on top of the representation, then it means that there does not exist any classifier which is good at training time but bad at test time. And essentially the if you put these two together, then you can say that V sufficient and V minimal representations are optimal in terms of the test error. And the experimental contributions of the paper is that if you optimize for V minimality, then it gives rise to a good regularizer for supervised learning. And the degree of V minimality of hidden layers is highly correlated with generalization. So if you take a trained network and you study how much V minimal the layers learned by the trained network are, then we see that how V minimal the hidden layer is well correlated with generalization. So this is the overview of the results from the paper. Um, and so the problem setup is as follows. So you and the company are going to play a three-stage game. And what the company does is that the company selects a priori a task which is defined by some joint distribution over x and y, where x are the images and y are the labels. The company selects a predictive family V, so which in our case previously was vertical decision boundaries, and the company is selecting a loss that they're going to use on top of the predictions, which is just going to be your log loss that you use in maximum likelihood learning, or
So,
like
Rama, so are we are going to do the regression also? Because we're looking into the, or just for the classification only?
yeah. So y here is categorical, so it can only be, it is only for classification.
Okay, it's
ఎవడో
on.
మాట్లాడాడు, అప్పుడు వాడితో మాట్లాడుతూ వెనక్కి వెళ్ళింది అనమాట.
Okay.
So yeah, essentially that. And so and also you provide like a so that your job is to provide a probabilistic encoder P of z given x. And then the company is going to do so given the specifications of the company, right? So you take those things as input and you provide a probabilistic encoder P of z given x, and then the company at evaluation time, so this is how the company would evaluate how good the representation is. The company would sample some finite samples from the joint distribution over x and y. So it would sample m data points from the joint distribution over x and y. So that's your data set. The company will then use the representation that we gave in the second step, and it would do empirical risk minimization. So that means that in the function family V, it would search for the parameters within the function family V that would minimize your empirical risk, which is essentially sum over all the data points that we sampled. Was there a question?
No, I think
రావట్లేదే, ఏమీ రావట్లేదు.
ఫోటో తీసారా?
We need to mute.
yeah, I muted him, but I think I unmuted again. So
Okay. Okay, so essentially then like so we sum over all the data points in D, and
so
what the company
I just want to ask, so I think you are taking this probabilistic sense P given z of x, so and I see this is a expected value, right? So it is in Bayesian framework, or you are doing for in the generalization? There is no it's a like a parametric form or non-parametric form?
There is a parametric encoder. So I mean, so in practice, in our experiments, right, so there will be some, you could have just like done something non-parametric, but what we do, and it's not conditional on being parametric or non-parametric, although I think it makes more sense for parametric. And what we do is parametric. So there is essentially going to be a neural network that's going to predict this density on Z given X.
Okay. And then
right, so,
the whole idea is that you want to estimate this true density, right?
Correct.
Oh, okay. Okay, thanks.
Yeah, so representation learning is the same as estimating that distribution.
Okay, thank you.
Yeah, and so this expectation we'll do using like Monte Carlo samples. So you just like take an image, you get the distribution, you sample from it, and then you compute your loss, and that's how you're doing empirical risk minimization, and then you get the classifier. And so then the company is going to use the estimated classifier and compute the actual risk on the data set. So that's the true risk. So if you see here, this is like some D sampled from a single D sampled from the joint distribution. The true risk is going to be the generalization error, right? So how well does this F that we found using empirical risk minimization do on, and the representation do on expectation over various data sets that we could have sampled. So that's your true risk. So that's your R. Does that make sense? So that basically, in very simple terms, you give the company a representation P of z given x. They evaluate the representation, and also they evaluate it by training first on top of that representation, and then checking what the test error is. And so the optimal representation we are saying is one such that if for all data sets and for all F stars, which are an empirical risk minimization for a data set and a given function family, we have that the test error is going to be the minimum possible test error for that F and Z. So what that means is that the fact that you were doing the estimation on, so it basically means that the fact that you were doing the estimation on finite samples from the joint distribution does not matter at this point, because the representation is optimal. If you do well on training, you'll also do well. So whatever risk you get on the training set, that is going to be the same risk that you will get on the test set. So in some ways, this turns statistical learning theory on its head, because usually in statistical learning theory, traditionally, we have a representation or some features, and then we ask what is the right function family to use on top of the features. And then we have notions of how to regularize and so on. Here we are saying that if your representation is optimal, then no matter, you don't need regularization. No matter what function family you use, no matter what member of a function family you use, you will always generalize. Any questions on this?
So, but I think the reason why it turns on its head, because you are doing in the probabilistic sense, right?
So the reason why it turns it on its head is not because of the probabilistic sense, but like usually if you're learning an SVM, right, then you would have all the data points. So your feature space is fixed. And then you are asking, oh, like among all the decision boundaries which separate my data points, you say that, oh, for generalization, max margin is good. So that is a particular way of selecting within the function family of linear classifiers in that feature space, if you're doing linear SVM. But here we are saying, even if you don't carefully select to maximize the margin or anything, you will still generalize, because you have the freedom to change the feature space. In an SVM, you don't have the freedom to change the feature space. So you assume the feature space is fixed and you ask, what is the right function in the feature space on top of the feature space. So then you say, okay, like select something with max margin. Here we are turning it on its head in the sense that we are changing the representation such that no matter what, even if you don't do like empirical risk minimization carefully, you will still generalize.
So maybe I think, I don't know, but it's because of the distribution is involved, or same things I am repeating in different way. Because of generalization we are able to do, because now it's a distribution, right?
Not just because you can learn that distribution.
Yes. Because see, the way Kate is there now, when you say specs or some things, so maybe it's a noise or something. So inherently you are learning that distributions. So the algorithm would have that or robust enough to ignore such things, or maybe to include such things, right?
Right. But I don't think the distribution is the key. It's the learning which is the key.
Okay. But you are learning the distribution, so that's why it is able to do.
Yeah.
Okay.
And so we'll give you some so we build on top of the information bottleneck principle. So I'll briefly go into a background on what the information bottleneck principle says and how our work connects to the information bottleneck. So firstly, the information bottleneck is a framework which says that a sufficient representation is such that you maximize the information with the labels. So if you have a representation Z and you have the labels Y, then if the labels do not have, so a sufficient representation is one that maximizes, does argmax over the representations to find the representation that can predict Y, that has a high mutual information with Y. So that just means that knowing Z, I should have some sense of what Y is, right? Informally, that is what mutual information is giving you. So you want to be predictive. And then it also defines a notion of like minimal sufficient representations. So what that means is that along with maximizing the mutual information with the labels, you also want to find the representation such that your information with your inputs is minimized among all the sufficient representations. So you do an argmin over the sufficient representations to find the representation that is essentially good at prediction while also being minimal. So a way to think about it is that if you give the original image itself as a representation, right? then the mutual information between the original image and the representation is going to be like 1, right? So it's going to be really high. I mean, like not 1, but like the entropy of the image distribution. So you'll have really high mutual information, but it's not minimal. So it like essentially you're going to have really high mutual information between the image and itself, and it's going to be predictive, but it's not going to be minimal because you want to minimize this mutual information. So essentially the principle here is that the simplest or the most succinct representation is good. And that is the intuition for the information bottleneck. And the way it is in practice implemented is as a Lagrangian relaxation of minimal sufficient representation. So you say that you have a term that encourages sufficiency, and you have a term that encourages minimality, and your objective function is an argmax over the representations of like the mutual information between Z and Y. So you want to have high mutual information between in the representation regarding the labels, minus beta times minimizing the mutual information between Z and X. So that is the minimality term. So instead of
you are evaluating I mean, you are mentioning maximizing minimizing information. So more or less, are you estimating the entropy or what?
Yeah, so this is the way you do it in practice is like so what would you do? You would pick I mean, there are obviously like some entropy terms here, right? So so you have entropy of, so mutual information between Z and Y is entropy of Y minus entropy of Y given Z. Entropy of Y is a constant for machine learning because entropy of Y depends only on your data distribution, not on your parameters of your representation, right? So based on that, you can like solve in the Gaussian case, you can solve for the exact parameters. In the case where, let's say, you have more general distributions that are parameterized by deep neural networks, people do variational approximations to these mutual information terms and then get algorithms that can fit this objective approximately in practice. So it depends on how you parameterize it, but essentially you are solving for this objective with respect to P of a probability distribution on Z given X. So you have some, you will check for, you basically you're trying to see for different P of Z given X, what is the sufficiency and minimality that you can get. And your goal is to find the right P of Z given X such that this is maximized. Was that clear? I can send references to like the deep learning versions and the Gaussian versions later if you're interested.
Yes, it is clear. Yeah. Okay.
Yeah. So the benefit of this is that in practice it has been shown. So information bottleneck has been shown to help improve generalization. The issue is that there are no optimality guarantees. So at best, although the principle has been around since 2000, we do not really have any strong optimality guarantees that information bottleneck leads, that minimal sufficient representations are optimal in some way. We don't really have strong statements of that nature. And the issue with mutual information is that it is notoriously hard to estimate from finite samples. So because in machine learning, we often don't know the true distribution. If we know the true distribution, then of like the true joint distribution of like two random variables, we can of course compute the mutual information. But it is also, if you don't have the true distributions, but you only have samples, if you don't have the true distribution, but you only have samples of the two random variables, then estimating mutual information terms like this and this are notoriously difficult. So these are the issues with the information bottleneck. And so there are also more fundamental issues with mutual information in machine learning. Our premise is that information bottleneck, which uses mutual information, is not suitable for machine learning. And the reason is that the mutual information can basically be written as so for in the machine learning context, it can basically be written as the following you can write it as a constant minus a minimization over a universal function family of the cross entropy of f of z and y, where f comes from a universal function family. And so it is like the best possible log loss you can achieve when predicting y from z with any classifier in a universal function family. And basically, this is straightforward to see. Like I was mentioning on the previous slide, the mutual information between y and z is defined as the mutual information is defined as the entropy of y minus the entropy of y given z. And so, as I said, in machine learning, because the data distribution is unknown and it's not what you do learning with, that is something you cannot change. So that's a constant. Minus, there is an expectation over z and y of log probability of y given z. So that's the entropy of like y given z. You can replace that with an optimization problem because you don't know the true probability density distribution of y given z. So because I could come up with any representation z, and you would not know the true y for that, then you can replace that with another minimization over a universal function family of the expectation over z and y of like minus log f of y given z. And because the log loss is there's a notion of like strict properness. So the log loss, when you will do this optimization, will recover the true distribution p because it's strictly proper. So basically, if you look at it, what we are like looking beyond all the math, what we are saying is that mutual information is like saying that from the representation, a good so for example, a sufficient representation is one where if I use the universal function family, I should be able to recover back the label. Right? Because you're searching over the universal function family to say that you should be able to predict the label y. And a sufficient representation will be one such that it supports you to decode the label y from that representation given a universal function family. But actually in machine learning, we never have access to the universal function family because like we discussed previously, maybe on top of the representation, you're using a linear classifier or you're using a 2-layer MLP or something like that. So that is a much smaller function family than the universal function family. So we are calling that function family as V, right? So we do not have access to the universal function family. We usually have minimization over a smaller function family. And so there is a notion of like V information where you, instead of looking at the mutual information, which sweeps over all functions that can go from like Z to Y, you only look at the subset V that you're going to use. So that is called V information. And that is basically very similar to the form of the mutual information you can see here, except that instead of using U, we are using V. And essentially everything else is the same. So now you say that in the function family V, we should be able to predict correctly the labels. And this has nice advantages because it has strong pack estimation guarantees and monotonic recoverability and things like that, which so the pack estimation guarantees are missing for mutual information. So this is like better in a machine learning context. And it is also more practical. Any questions on this? Okay. And so essentially, intuitively, we can understand what the information bottleneck does is as follows. So sufficiency in the information bottleneck means that, you know, there are like some classifiers which can distinguish between the two classes. And minimality means that there exists no classifier which cannot distinguish, no classifier can distinguish within a class. So that means, sorry, this is wrong. No classifier can distinguish within a class. So even if you search in the universal function family, there will not exist any classifier that can distinguish between all the entities of the same class. And in practice, that's going to happen when, like, you know, one way that can happen is if like all your cats collapse to the same point and all your dogs collapse to the same point in some feature space. So one issue is that with sufficiency is that because you're searching in the universal function family, the classifiers that we might be working with may not be powerful enough to distinguish between the two classes. And minimality, the issue with minimality in the information bottleneck is that you are asking, because instead of saying that let us just make sure that for the function family, let's say vertical decision boundary that we are using, let us make sure that we cannot distinguish within and members of the same class. Instead of being practical like that, you are saying no matter what function I use, you should not be able to distinguish, which means that you have to do more work. You are solving a much harder problem than you care about solving. And so the sort of our idea here is to use this idea of like V information to define what sufficiency and minimality should look like, and to then get like optimal representations. And so this is what we call as the decodable information bottleneck. So the key intuition here is like what we said previously. We want to use V information instead, which considers the function family V, instead of the mutual information which the information bottleneck uses. So now if you just look at the information bottleneck equation, we could just replace V and get a new objective that looks like this. So now you say that instead of the mutual information, you want to maximize the V information of the representation with respect to the labels, minus beta times the V information of the representation with the image. So you want something that is very similar to IB, but replaces V information with mutual information. The issue is that while we can just write it, there is no such thing as the V information between Z and X, because the V is a function family, if you remember, that goes from, so let's say your representation is, so if you have like your images, which are like the cat and dog classification, let's say your images are 128 by 128. Then X lives in 128 by 128 by 3 dimensions. But V, which is the function family we are using for classification, it can only predict in 2 dimensions because we only have 2 labels, right? So there is no such thing as the V information between Z and X. It's not really defined. While the V information between Z and Y is defined because that's the function family we are using. V is like, let's say if your representation is 256 dimensional, then your predictions are, let's say 2 dimensional, then V is going from 256 dimensions to 2 dimensions. And so with a 2 dimensional output, we cannot predict like something that is 128 by 128 dimensional. Do you, are there any questions on this? Okay. Is it clear?
I think so. There is no question at present.
Okay. And so what we do is we define, so the way we do this V information between Z and X is that we define what is called as like the Y decomposition of X. And informally, what that means is that we decompose X into multiple N's, which random variables N's, which take value in cal Y, which is the space of Y's. So here it would be like two-dimensional space, right? So 2-dimensional Rn, so R2. So we will decompose the X into multiple N's, which take values in R2. And the intuition here is that N is like one possible labeling of all examples with the same underlying label. And then the way we do it is that the V information is then defined as the average over all possible. So you decompose X into a given N, which takes values in Y. Then you can compute IV of Z to N, because you can compute this because now N, instead of X, N now takes values in Y, which is where V also predicts. And then the actual minimality term is going to be average over all possible such choices of N. And so this is a generalization of the idea of V information into any codomain of V. And so the decodable information bottleneck objective is essentially as follows. So you do argmax over the mutual information between Z and Y with respect to the function family V. So this is V sufficiency. And then your minimality term is the V information of Z with all possible decompositions of X. So that is what we call as the V minimality. And the good thing here is that the decompositions of X are in the codomain of V. So you can actually predict and estimate those things in practice. So there are numerous benefits of this. It guarantees optimality. It can be well estimated from samples if V is not too large. So we have some estimation bounds. And it recovers information bottleneck when V is equal to U. This is straightforward to see because if you replace V with U, then like actually also the minimality term that also recovers like the mutual information. So this is like a strict generalization of information bottleneck with respect to the V function family. The other issue is that this leads to a min-max optimization, which can be tricky to deal with in practice. So because actually here there is an argmax over Z, but there is also a minimization inside this like decomposition term. So in practice, so if you stayed with like all the maths so far, here's a more intuitive explanation of like what the framework is essentially saying. So V sufficiency means that you should be able to predict the real labeling that you have. So imagine you have these cat and dog image examples, and you are saying that the encoder should be such that from the representation Z, using the function family V, you should be able to predict cat, dog with the right labels. So that part is straightforward. That is what you would do normally also when you're doing any supervised machine learning task. And then V minimality basically means that with the function family V, I'm going to now consider one random labeling of like different dogs. So let's say you have dogs which have like, you have this dog which has glasses, mustache, and like this bow tie. Then using the function family V, I should not be able to distinguish between all these dogs which are having different intra-class variations, not inter-class variations. And then you would pick some other random labeling on cats where you would label them as like A, B, B, A, or something like that. And then you would ensure that you are not able to solve this optimization problem well, this learning problem well. And then you would ensure like similarly like this for every possible binary labeling that you could come up with on all the members of a given class, you ensure that the representation Z is not able to learn or fit those random labelings. And so in practice, the way we do it is by first solving each of these each of these optimization problems in the inner loop where you try to fit as well as possible with V each of these random labelings, and then you reverse the gradients into the encoder to get a representation Z such that essentially you are able to get a representation Z that is going to distinguish between cats and dogs, and it is going to be unable to learn any of these other classification problems that we came up with in the process of estimating V minimality. And we also have approximations. Yeah, was there a question?
The way the problem appears, it looks like see this adversarial attack. So it will be immune to adversarial attack also, right?
It could be. We haven't actually tested that, but we expect that it should help with adversarial attacks also.
Because the way minimality is telling that you can't do the interclass, right?
Yeah.
So if I can put some page or something, I don't know. This is just like intuition.
Yeah, we also think that it should help with adversarial attacks. I agree.
Okay.
Yeah.
Okay, thanks.
Yeah. And so this is how you would do it with neural networks. But like nothing in the paper actually says that this can only be done with neural networks. This is as general as information bottleneck. So as long as you have some function family V, and it could be parametric, non-parametric, we don't care. But as long as you have some class of functions, we can like apply this framework. So coming to the experiments. So the first question we ask is, does approximate V minimality ensure generalization? So what that means is that we compare with like on a CIFAR 10, on the CIFAR 10 data set, we are showing here like the log likelihoods where the standard deviations, so where the error bars are like computed over 5 runs. So you see that our framework leads to a regularizer that is fairly good compared to like some of the other regularizers that people use typically. So for example, we are comparing to dropout, like weight decay, which is like a regularizer on the L2 norm of the weights of the network, VIB, which is the variational approximation to the information bottleneck that I was talking about earlier. So we compare to all of these and we find that our regularizer is competitive in terms of test log likelihoods compared to like all of these previous approaches. There is a small note. None of the previous regularizers were proposed in the regime where you tested them in the 2-stage game setting, where like, you know, the game between the company and you, where you give them the presentation and then they fit the V. So none of these previous methods were proposed in that setting. So this is definitely like results in a setting which are like closer to where we actually care about doing well. But like in general, this is a useful enough regularizer. And then the other question is like, what are the consequences of being minimal with respect to the wrong V? So what I mean by that is that, let's say I do my sufficiency with one function family. Let's say I'm sufficient with respect to a V, which is 2-layer MLP. But when I do minimality, I pick some other function family to be minimal with respect to. Maybe I'm minimal with respect to a 3-layer MLP, or I'm minimal with respect to a linear function family. Whereas here I'm going to use a 2-layer MLP. So we also study what is the consequence of being minimal with respect to the wrong function family. And so what that basically looks like is that you get the best performance when you use the right function family, and then when there is a mismatch in the function family that you are minimal with respect to, then your performance is worse. So you get best performance when you pick the same function family to be sufficient and minimal, which makes sense and validates what we are doing. Also, to note that information bottleneck uses minimality with respect to the universal function family. So that is like saying that instead of using V, so V plus is a bigger function family, and the universal function family is even bigger than the V plus function family. And you can see that the results in that regime are much worse. So this is like qualitatively saying that experimentally also you see that you need to do V information as opposed to mutual information, which uses the universal function family. And then like here are some intuitions for like how does V minimality ensure generalization. So assume that we have some version of CIFAR 10 where you have MNIST digits labeled on top of them, right? And so here the labels are the true labels of the CIFAR 10 dataset, and the distractors are the MNIST digit labels. So you can see that the performance, so as the degree of V minimality increases, you are able on like, so as the degree of V minimality increases, so firstly, you are doing, so the first curve here, if you look at CIFAR 10 training, then the performance on CIFAR 10 training decreases as we try to make it too too minimal, right? So for a range of minimal representations, you're able to still predict the correct label on training. But after a point, it gets much worse. But as the degree of minimality increases, you see that the test performance improves. So as you get more and more minimal representations on the x-axis, your test performance goes up. So that means that the generalization gap, which is the difference between the training and test, is reducing as you get more and more minimal. On the other hand, we also notice that if we then try to use the representation to predict MNIST labels, so remember the original task is CFAR labels, but if using the representation, we try to predict like MNIST labels, we see that as the representation becomes more minimal on the x-axis, the log likelihood decreases for the MNIST test and MNIST train. So it means that any excess information that the representation was having that was pertaining to the MNIST digits is being removed as you become more and more V minimal. So this is giving you an intuition of like how the information is being removed in this process. We also show that this V minimality thing can be used to predict the generalization of a trained model. So here the encoding need not be stochastic. You can just train any supervised deep neural network, and you can use V minimality you can probe the V minimality of a hidden layer of this deep neural network. So here we see that on like the tau accuracy, tau log likelihood, these are all measuring like uh, how correlated a given measure is with the actual generalization. So what that means is that if I take a deep neural network and I compute the entropy of its output distribution, then that's my measure. And then I'm going to compute in each of these rows, I'm going to compute that the correlation of the entropy of the output distribution with the actual generalization values that I observe. So, and then like those correlations are what are being reported. So this has been used to like sort of build an understanding in previous work. It's been used to build an understanding of like why neural networks generalize from an empirical perspective. And here we see that compared to some of the best sort of generalization measures that are discussed in this previous work, our framework of V minimality actually yields very strong correlations with the actual generalization that we observe. So this is one of the best generalization measures that we know for deep learning yielded by our paper. And this is like the correlation here is a rank correlation evaluated over 562 CNN models using a re-implementation of the previous paper. Yeah, and so there are some future interesting directions. I think it's interesting to think about how to explain deep learning with and stochastic gradient descent with deep codable information bottleneck. Like we think that people have been talking about implicit regularization in deep learning. We think that somehow stochastic gradient descent might be doing a version of decodable information bottleneck, because these results, none of these models were actually using decodable information bottleneck. They were just using gradient descent with stochastic gradient descent with like deep networks. And it seems like minimality is still correlated. So how do you explain that? What is the right way to optimize V minimality to solve the minimax problem in a more efficient way? And then like none of these networks, as I said, are like exactly V minimal. They're approximately V minimal. So we don't have all of the guarantees in our paper are for exact V minimality, but not for approximate V minimality. So that is also something that needs to be understood better based on our results. And then there are various applications to like self-supervised learning, multitask learning, and so on, where this framework could be useful. So in general, we believe that the results of this paper are fairly generic, and this could find application in a whole different set of areas of machine learning. And so, yeah, thank you. And I'm happy to take